Hi guys, today I'm going to talk about ionic bonds. Now, before we talk about ionic bonds, we have to talk about the SBPE, the soft board pigeon egg, the structure bonding particles energy of ionic compounds. Now, from our secondary school, we know that the structure of ionic bonds is a giant ionic structure. They're bonding, they are held together by strong electrostatic forces of attraction. Particles, they consist of lattice of cations and anions, and energy equals a lot of energy. Now let's look at a new concept, the coordination number. It is the number of ions that immediately surround an ion of the opposite charge within a crystal lattice. More ions can be packed around a larger ion. It means if the ion has a larger size, then we know that electron are the same size. Okay, so since electrons are the same size, this one, for example, this one is like a sodium ion or something, and this one is like a calcium ion or something. See, more electrons can be packed around it. Yeah, so the larger the size, the higher the coordination number. Now let's get the factors affecting ionic bond strength. Now this is a very important formula. The modulus of the lattice energy is directly proportional to the modulus of the product of the charge of the cation and anion over the sum of the radius of the cation and anion. Now, to get the product of ionic charge. The larger ionic charge, the larger the magnitude of lattice energy. And the larger the sum of ionic radii, the smaller magnitude of lattice energy. It means this one is directly proportional and this one is inversely proportional. We can see from the formula as well. And the product of ionic charge usually accounts for a larger factor. So even if the ionic radii is larger, right? But if the product of ionic charge is larger, because it's a product, so it's generally larger. So we see that lattice energy generally increases. Then explaining and comparing the melting points of ionic compounds. First, we have to quote the structure of the compound. Alright, this one is ionic compound, right? Since you're comparing ionic compounds, you first have to say, yeah, they have a giant ionic structure. Then you have to quote the LE formula. Then compare the ionic charges. Then compare the ionic radii. Then deduce how the ionic charge ionic radii affect the strength of ionic bonds using the LE. Then discuss the energy required to overcome the ionic bonds. Okay. Now let's look at physical properties of ionic compounds. An ionic compound is solid at room temperature because they have very high melting and boiling point. A lot of energy is needed to overcome the strong electrostatic forces of attraction between the cations and anions. Be a bit more specific now. Okay, since we are in JC, you have to say between what cations, between what anions. Basically, right, if you know the compound, right, you have to state what cation, what anion. Okay, in the giant ionic lattice during melting and boiling. Okay, so the stronger ion bond higher melting and boiling point. Now let's get hard and brittle. Ionic compounds are hard because every ion is strongly attracted by the oppositely charged ions surrounding it. Right, they are also brittle, means they break very easily. Okay, so when little stress is applied, the ion gets displaced because you see the ion, right, in a giant ionic lattice structure, something like this, sort of like a metallic lah, but not really. Then it has its layers like this, right? Then when little stress is applied, right, they get displaced. When they get displaced, right, then they have a similar charge come together, they repel each other, then the giant ionic lattice just breaks down. Okay, so they fall apart. Okay, let's look at the solubility. Ionic compounds can be soluble or insoluble in water. Now let's get sodium chloride lah. Sodium chloride is soluble in water because it forms ion dipole interaction with water. So basically, the O, right, then the dipole interaction here, positive, then O, then sodium chloride is soluble in water because the energy released when Na plus form strong ion dipole interaction with H2O is sufficient to overcome the energy needed to build a strong electrostatic attraction between Na plus and Cl minus ion and also the hydrogen bonds in H2O. Then, in illustrating ion dipole interaction via diagram, draw the ion, complete sets of partial transitions on H2O molecules, hash lines, and ion dipole interaction. Now let's look at electrical conductivity. Ion compounds are not conducted in solid state because they are good conductor in the molten aqueous state. In solid state, the ions are held together in a giant ionic lattice by strong electricity and can only vibrate about a fixed position. Then they are not mobile. But whereas in a molten aqueous state, the lattice is broken down, the ion becomes mobile and are able to act as mobile charge carriers and conduct electricity.